Bahram. Thank you. Yeah, thanks very much for having me and for organizing the visit also to Tingy. I hope what I've put together will be of interest to you. I'm going to try to span a fairly large range of type of science that can be summarized with the title that I've given you. We identify ourselves as nano-optics people, basically wanting to understand nano-optical phenomenon at the fundamental level, so at the single atom, single molecule, single photon level. And I think the work has grown to have some also connection to applications, but our usual kind of motivation is not very directly application driven. So let me see how I can move around here. I have to click on the mouse. Yeah, so just to orient you, this is Germany, and this is Munich, and this is Frankfurt, and that's Berlin. This is a 2-hour train ride, and this is a 2-hour train ride. So we're right there, but places like Prague and Vienna are also quite close. Now, Erlangen is a small town, but it's a seat to many global companies like Siemens and Adidas and Puma and a few other ones. Our institute was established fairly recently in 2009. As Bahram said, I joined in 2011. And we have since extended our work and are building this building where we try to connect fundamental physics and fundamental medical research together. So not so much doing medical physics or medical technology, but really trying to do basic research in medicine, but with physical and mathematical techniques and concepts. I'd like to also flash, just because we're in a, as Bahram said, #1 public university in the United States, so lots of amazing talent. We are, I'd like to advertise a little bit, and it's not necessarily for you guys sitting here, but if you spread the word, we have a new graduate program that now, traditionally the graduate work in Europe was quite different from the one in the States, but now it's somewhat conformed. So if people are interested in studying right after bachelor, then I think we have an attractive program that we can offer. People who work with me, I'd like to thank them ahead of time, just in case at the end I might not get a chance to do that. So in the nano quantum optics area, there are people with the permanent position in my group, and postdocs and PhD students. We are looking for postdocs there, so if you identify yourself as someone who might like to do this type of work, please do that. My group has grown to be more gravitating towards biophysics over the years, and so in the other part of the group, again, we have some permanent researchers and postdocs and PhD students. So as you see, we're quite international. The working language is German or English, depending on who you are talking to at that time. So with that little bit of an advertising about where we come from and what we do, I'd like to jump right in and try to motivate you for the kind of work that we do. The first part of the talk will be more on quantum optics, laser spectroscopy type of thing, and the second part will try to bridge to more biophysical applications and studies. So let me start by thinking about microelectronics and realizing that a typical circuit that you would have has almost a handful of important components that then just get repeated, and you have different types of functionalities. So you obviously need sources, and you have transistors and capacitors and resistors and all of that. And basically, what we would like to do, and we're by far not alone in the world, is to see whether you can come up with something like a quantum optical circuit. So the idea of having optical circuits is now 50, 60 years old, but the idea of having a quantum optical circuit is fairly new, and it's still quite out of reach. But basically, the idea then would be that you would get this type of circuit, and you would have to find a replacement for each one of these elements that is optical. And of course, it would have to be miniaturizable, but also working in the quantum regime and not in the classical regime. So if you can do a little bit of any of these things, then you're doing very well right now in the general area of quantum engineering. So as I mentioned before, one of the important elements is having sources, and if you want to do things optically and you want to do this quantum optically, then you definitely need to have photons. And if you have a normal laser, then that laser doesn't produce quantum light. That light is pretty much classical, but you would have to find ways to generate non-classical sources of light. So that's one big task that is very far from being done these days. But then you also want to have these other elements, and the fundamental kind of qubits that people do want to use are things like individual atoms and molecules. So over the years, people have learned how to manipulate and control individual atoms and molecules. But when I went to graduate school, this wasn't done at all. So you still had talked about individual atoms in your textbook, but never in the lab. Meanwhile, this is has advanced a great deal, but we're still struggling in the field to get sufficient control over individual quantum emitters. The quantum emitter that we have been using in the lab is our dye molecules. And I'm gonna, over the next few slides, introduce you to the system. The molecules that you would know, dye molecules, you don't think of them necessarily as quantum emitters. And those are dye molecules that you would use, for example, in fluorescence microscopy. Seeing individual dye molecules was a big deal, and it was an important step towards a Nobel Prize in 2014. If you look at any of these molecules, basically you have an electronic ground state, electronic excited state, but you also have vibrational levels associated with both of those, which means that you have a number of different transitions that you can use. Usually one illuminates a dye with high energy, for example, green, and then there's a decay via these different channels that is at lower energy, for example, in the red. As far as the chemistry is concerned, the dye molecule kind of looks like that. So you have a lot of carbon rings, but usually these dyes also have nitrogen, oxygen. This is the kind of dye that you might be familiar with. And as you will see, this is not the kind of dye that we use for more of a quantum optical study. But it was a breakthrough in the early 90s to be able to detect individual dye molecules at all. So not so much because they're quantum emitters, but because you're improving your detection sensitivity so that you don't need a large number of molecules to get a signal, but even a single molecule. And what you just saw here is a typical microscope, fluorescence microscope image that you now might have in your undergraduate lab course, where you can see that you can have sensitivity to see individual dye molecules. These molecules usually are not very nice for kind of difficult experiments, partly because they photo bleach very fast, and also they might photo blink. There was, at the same time, in fact, the very first report on studies on single molecules came from the group of W.E. Murnau, who was at the time at IBM. And this is done in a slightly different type of molecule. Still, you have a lot of carbon rings, but then other than carbon and some hydrogen passivation, you don't have anything else. These molecules happen to be much more rigid, and their vibrations are much more confined, and it turns out that they end up having very strong optical transitions. And now if you embed molecules like that in an organic crystal, for example, anthracene, and this is a contour of an anthracene crystal that you see here, then you go to low temperatures, and we're talking about something of the order of 2 or less Kelvin. What you can do is you can detect individual molecules in frequency space. So now the point is that each molecule in the crystal sees a slightly different local environment so that their frequencies are slightly shifted from each other. You don't know exactly why, which one, but that's just, there's a certain distribution, which means that you go to very low temperatures so that each one of these lines becomes very narrow, and therefore the neighbors don't overlap. And now if you scan your frequency cross, then you can talk to individual molecules at a given time. So this system was actually studied quite a bit in the early days, also in the 80s, partly for optical storage, because this would give you an incredible amount of kind of optical capacity. But that hasn't been realized yet in that form. So anyhow, so if you scan, for example, this particular dye molecule that I'm talking about is nice, and we work a lot with it because it's in the Ti sapphire frequency range. And you see here that scanning somewhere from 746 to 743 nanometers, so over a fairly large range in the spectrum, you might find molecules all over the place. And if you look again, because the matrix, if you want this kind of artist point of view, is not identical, the lattice is not perfect. If you look around here, then you see all kinds of different molecules. But if you zoom into any of these things, you see that you have a very nice narrow Lorentzian shape. And the line width that you have here now is extremely narrow. It's of the order of a few tens of megahertz. And this line width is exactly what you would expect also from an atom in vacuum. Usually when you put molecules or atoms in a solid, there's a very large interaction because of coupling to phonons in the solid, so that the line becomes very broad. By going to very low temperature and having the right matrix, you can make this line basically collapse down to its natural line width. And what we mean by natural line width is that this line width is what you expect from a Fourier transform of the lifetime of the excited state. So the excited state lives for about 4 or 5 nanoseconds. And if you do 1/2 pi that lifetime, you get something of the order of several tens of megahertz. So there is no dephasing, there is no kind of impurity in this line. And that's why it's a good system for doing quantum optics. All right, now the experiments that were done in the first 2 decades or more, 2.5 decades, they all detected molecules via fluorescence. That means that you usually excite the molecule here and then watch the photons that are emitted on this other transition. And they're redshifted, so that means that if you put a spectral filter, you very nicely detect these photons on almost no background. So you get an incredible signal to noise ratio by even detecting a single molecule. But what happens now is that you don't have any phase information. because this is a random process. The emission from the excited state is a random process. So there is the phase of this photon has absolutely nothing to do with the phase of the photon with which you excited. And if you want to do quantum optics, you would like to keep the phase, because that phase then would also be reporting about the phase of the wave function in the atom. So the question is, what happens if you don't use fluorescence, but really think about something very basic, that is, you have a two-level atom, and you send a photon onto it? What's going to happen? Well, this photon is going to excite the atom, but it's not going to stay there for a very long time. It's going to come back again. And now the question is, what is the probability of the interaction between these two? And because if you could have a large interaction, then you wouldn't have to use fluorescence to look at it. You could just use normal extinction. If you look in your textbook, you see that the cross section of a two-level atom or a point dipole is actually incredibly large. So this is essentially of the order of lambda squared divided by 2. That means that a single atom has an optical cross section that is, an atom is about, let's say, an angstrom, so 1/10 of a nanometer, but the cross section is a few hundred nanometers large. Okay. Now, the point of cross section is that that's the surface area to which you could focus or confine your light, and then make sure that that light interacts with your atom. Okay. So the question now is, can I then focus my light down to something of the order of lambda squared divided by 2, so that a single photon coming onto the atom would interact with it with 100% efficiency? It sounds like a very, very basic thing that you shouldn't be dealing with in the 21st century. But if you think about what it means to do this experiment, you will find out that it's a difficult experiment to do. You have to first pick your type of atom and then see how you can do this experiment. And you will see that it's always kind of tough. So our atom was a molecule, and the kind of molecule that I told you. So we're working in the cryostat, and now we have to focus very tightly. Already focusing down to the diffraction limit in the cryostat is tough, because the optics that you have, nice objectives that you would buy from Nikon or Olympus, doesn't work in the cryostat. So you have to come up with your own idea of how to focus very tightly. The answer is actually quite simple. You can take a half-ball lens and use that as a solid immersion medium. And then you can use a normal aspheric lens. And when you put the two together, you can focus down to something of the order of lambda divided by 2. So many years ago, more than 15 years ago, we started an experiment like that. This type of thing in the cryostat is somewhat tedious, because you have to have a lot of degrees of freedom to move things around, but it's all doable. So then what we showed was that indeed, if you could focus your light onto the system and scan the frequency across, now as your frequency went over the resonance of one molecule, you would get a dip in transmission that would be sizable, of the order of 10%. Now, a 10% dip, that means that you have a single atom and you put it in your laser beam and you look at it, and just one atom would attenuate the light beam by 10%. Okay. So this was the largest kind of effect that anyone had seen from a single atom in this simple experiment. And it shows that really this kind of thing does work, but it's not 100%. It's only of the order of 10%. We've done a number of studies taking advantage of this very efficient interaction of single photons with molecules. Besides the physics, the underlying physics, before I go on. this is an extinction process, and an extinction process is a very fundamental kind of process in physics. It's an interference effect. Okay, so you come with something like a plane wave. A focused beam is not a plane wave, but in the focus you can think of it kind of roughly as a plane wave. But your atom emits or radiates or scatters light, but it does that as a dipole because the transition that you have is a dipolar transition. So when an atom emits, it doesn't emit in all directions, but it emits like a dipole. So it would look kind of like this. Now, when you put an atom in front of a beam, what you have in transmission is the interference of the light that is coming and the light that is scattered by the atom. It's a very simple kind of textbook problem. And that means that the total intensity that you detect is the sum of the intensities plus the cross term, which is called the extinction term. And because of the way the phases work out, you get a destructive interference in the forward direction. In the hand waving type of argument, usually you think of this as an absorption process. But remember that you have a two-level atom. The two-level atom never absorbs. It takes light and gives it back. It doesn't take light away from anything. So it does redistribute the light, but mostly it's this interference effect that gives you this extinction in the forward direction. This is a very, very simple idea, but it's worth understanding it and appreciating it. And I'll use it again in the last part of my talk.
Next slide.
Yeah.
So you have a asymmetry along the x direction center, right? Where does the asymmetry come from? Everything goes symmetric.
The asymmetry is the direction of
Oh,
this guy coming, right? Yeah.
Excitation is going to the right.
Right. Now I said that, you know, if you want to do something like a quantum optical circuit, then you want to be able to send one photon onto one atom and make them interact. And that interaction is supposed to be part of your operation. But you have to have a very high fidelity. So the question is, what does it take for one photon to really have an interaction with a very high fidelity with a single qubit, with a single atom? And I showed that in a simple way, you can get 10%. 10% is remarkably high, but it's very, very far from 100%. It's no good for operations. So if we now go back to the molecule and say, why is it 10%? Well, it's because our molecule is not a two-level system. The formula that I gave you was if you only had two levels, but you see here that if the molecule gets excited, it can emit via all these different channels, and these all act as like a loss, so they reduce my efficiency. To get that back, what you can do is you can put the molecule in a cavity and enhance the transition that you like. You like this transition and not these other guys. And so the whole field of cavity quantum electrodynamics has been now about more than 40 years old. And what we're doing now is we're drawing on that. And the idea is that if you can enhance this transition by a factor of 10, then the act of, or the effect of these other transitions becomes negligible. So you're forcing the system to behave like a two-level system, because this transition becomes so fast that these guys don't get much of a chance to really do anything. So the way to think about what happens to a molecule in a cavity or an atom in a cavity is that you send a photon in and the photon gets focused. So this part is just like what we had before. There is a certain probability of interaction, which is given by sigma divided by A. But now the photon goes through, comes back and does it again and keeps doing it. And it does this by essentially the finesse. So if you get up to a finesse of 10,000, 50,000, you're increasing this efficiency by that much. The thing though is that when you put your, when you start with the cavity, this A becomes a lot larger than in a diffraction limited focus. So you lose in A and win in finesse. So you have to see whether at the end you win or not, but this is basically the enhancement factor that you have. You can rewrite that. That's another way of writing is the Q factor divided by the mode volume. And this is what is known as the Purcell factor. You might have come across. So, okay, you can also write it in terms of cooperativity that is quite often used in quantum optics. So basically now what you would like to do is you want to make Q as large as possible and V as small as possible. And making V as small as possible is particularly good because you don't really want to have a super high Q because you lose in bandwidth. So ideally you want to keep your Q as little as possible and still have a large enhancement factor. So when we started this work, we insisted that we wanted to have the smallest cavities that we can make. And the idea was then, because when you think about the concept and practicality of it, this is what we've done. We thought that we wanted to have a flat reflecting mirror, dielectric mirror. You put a thin crystal like that on the flat mirror. That crystal has doping of the molecules that we like. And now we want to bring a curved mirror on the other side and make a Fabry-Perot cavity. But now you want to make this curved mirror as little as possible so that you can bring it as close as possible and have a mode volume that is as little as possible. Okay. So that's kind of the geometry that we want to have. So we used focused ion beam milling in our own clean room to carve a mirror that has a radius of curvature of the order of a few microns. And of course, your mirror also has to be extremely smooth so that it doesn't scatter. So this is something that we did about 6-7 years ago. And so now we know how to make these mirrors. We send them to be coated with many layers of dielectrics to make them highly reflecting. So these then become 99.996% reflectivity. The flat mirror is the same. Now you put them together and you want to make a cavity that kind of looks like that. Because we want to bring this and position it, we actually put this curved mirror at the end of something like a tip. We either use an AFM tip or use an optical fiber and mill the end of the optical fiber so that we can position it and bring it very close to the place that we want. Basically, if you think about now, zoom into this cavity situation, the mode of the cavity here is only about a micron. So you want to be able to position your molecule right at the antinode of the cavity. So you want to have X, Y, and of course, Z capability.
What was the material of the mirror?
So in the case of the AFM tip was silicon, and in the case of the optical fiber, it's really just optical fiber. It's glass. So if we then look at our cavity, we see that in transmission, there is a resonance, and in reflection, there is a resonance. This resonance is now only a couple of gigahertz narrow, and that gives you a finesse just a little less than 20,000, and a Q that is about 140,000. And now if you tune the cavity to one of the molecules in the sample, so that the resonance of the molecule is resonant with the resonance of the cavity, then you see that the transmission of the cavity is completely changed. Okay, so intuitively, when you want to think about this, is that the index of refraction of a single molecule is so large that completely detunes the resonance of the cavity. So what was transmitted before is now completely not transmitting light, and vice versa. Okay, and when you go into the details, you see that in fact we have 99% coupling. So if you send a photon, you can reflect the photon with 99% probability.
And we also then did this experiment. I mean, all the details are written in this paper. In this paper, we also showed that we can replace now our laser with a single photon source. One of the best ways of having a source of single photons is to have a single emitter, because a single emitter can only emit photon at a time, because you excite it and it emits a photon, but it can't emit two photons at the same time. So it has to wait to get excited again to send the next photon.
How do you know you only have one molecule?
Right. So there are a number of checks that you can do, and in the 90s, this was kind of a big deal that you always have to prove that you have a single molecule. In our case, so the real proof is when you actually look at the photon statistics. If you do an autocorrelation measurement on the photons that are emitted, if you go to a very short time towards time delay 0, you should not get two photons coming at the same time. And then that shows that it's only one. If you're two molecules, because they're emitting independently, your autocorrelation never goes to 0. So the so-called anti-bunching doesn't happen.
You just look at the emission line width, right? You should be able to tell.
Exactly.
A single molecule should be single molecule. If not, you have inhomogeneous broadening.
That's exactly right. So in practice, that's how we do it, because it's much faster to do that. If you really want to be pure and convince 5 referees, then you also do a G2 measurement. But in practice, that's a very good check, because especially if your doping is such that the probability of two molecules being right on top of each other and fooling you is very small. So in this experiment, what we're doing is we're using a single molecule to emit single photons and take these single photons to the other molecule in the microcavity. And so that's one of the more complicated experiments that we've done. It couples 2 labs and 2 cryostats. So in one cryostat, we have the whole machinery that I just told you, with the microcavity and all the degrees of freedom and the molecule in it and all of that. But in the other lab, we have a similar type of cryostat, but here we just use molecules and collect the light that's emitted by a molecule, couple it to a fiber, bring it to this other lab, and at this point bypass the whole laser system and just directly go. So this is really just to show that the technology of coupling single photons and single atoms or single molecules is now, let's say, there. It's not very practical. This is not device yet, but in terms of fundamental kind of issues, this is nowadays doable in the lab. You can take your cavity to go a little farther if you increase the Q into the so-called strong coupling regime, where a molecule and the cavity kind of hybridize, in the sense that the same way that 2 pendula hybridize. And if you take 2 pendula at the same resonance and couple them, then you see that they do a splitting in the resonance. And so now you can think that there is one resonator, that's the molecule, there's another resonator, that's the microcavity, and when they couple very strongly to each other, the line gets split. And this is the line splitting that you see here, is so-called Rabi splitting. So an empty cavity would look like this, but if you have a strong coupling, then you get this splitting. In the time domain, you see that an empty cavity just has a ring down that's exponential, but in this system, you get oscillations. If you were deeper in this regime, you would get many oscillations here, okay? So basically what it means is that a photon comes out of the molecule, goes into the cavity, but before it has a chance to get lost, it comes back and interacts with the molecule again, and it can do this many, many times. So this is also a regime that we could reach, and that really brings you to a point where you can have single photon nonlinearity. That means that a single photon has such a large effect that can saturate the atom and bring it to a nonlinear regime. And so in this work, we showed, for example, that you can have a single photon switch which is also a desirable kind of operation that you want if you want to do quantum optical circuits. Again, we're very far from having a proper useful device, but we're showing that these basic ideas are now more within reach in the lab. Now, to go into more of a scalable, practical thing, we have to miniaturize things and put them on a chip. So now we have been working on a project for a few years where we try to do everything that I've shown you, but all on a chip. So our chips are not silicon-based because we're working around 700 nanometers. So they're glass chips. So just jump to one of the newest results that we have. This is a simple circuit that we have. So here's a grating coupler, a waveguide, another grating coupler, and now in the middle you can have a ring resonator or a disc resonator, and then you have another waveguide on the other side that can couple to this resonator. What you see in the background also are some electrodes that we can use to, and I'll tell you why we have them. This resonator is now only a few microns in width. That means that the free spectral range of that resonator is really very large. There are several nanometers. So you have one resonance and it takes several nanometers. There's no resonance anymore. So it's an extremely tiny kind of micro resonator. And what you can now do is, or what we do is we have learned how to prepare molecules on top of this resonator so that they couple evanescently to the mode of the resonator. And that means that if we now look at the transmission of this resonator, zooming into one of those resonances that I showed you, this is the resonance of the microcavity. And on top of that, again, you see that there is one molecule that is changing the transmission substantially. In this case, this is not coming down yet as much as we want it. We need to work on the quality factor a little bit, but you see that we're getting to the same kind of effect. These are all this dibenzotyrrolene molecule. It's a certain kind of aromatic ring type of molecule that the only thing that's special about it is that it has a resonance in the Ti-Sapphire range so that we can work with Ti-Sapphire. We did 20 years of work with dye lasers with other molecules that were more in the orange-red regime. And this one brings us to Ti-Sapphire. They're all of about the same family, the one that I showed in the beginning. You can definitely use, exactly, but rubidium works well when it's in the gas phase, but if you were to put rubidium on a solid, it would lose its character.
You put, you said it's tellurine, hydrocarbon?
Terylene, yeah.
So is it you put on the surface of the plant, or you put inside the liquid?
Actually, these molecules always want to be so far embedded in an organic crystal. So we grow a very small, very thin layer of organic crystal that includes these molecules as doping on the circuit. The waveguide itself is titanium dioxide. And we put this on top, yes. Exactly. So you see also that there are several other molecules that are kind of coming in, and where we actually want to go is we want to couple many molecules to the same mode to try to scale up and be able to have a photon interact with many molecules at the same time. And that's where our electrodes come in. So this is another recording where you see that there are these molecules. Many of them are coupled fairly well. And now if you put those, put an electric field on those electrodes, because these molecules are all within the resonance, but they're sitting in different places on the resonator, you can tune them with respect to each other. And you can see, for example, here that this molecule kind of stays where it is, but this one is tuned around it. And somewhere around here, you can actually put them on top of each other. And that's kind of where we stand right now.
showing that we can couple two molecules efficiently to each other via the mode of the resonator. So I don't know how I'm doing in time. I've spoken very slowly. I try to go a lot faster, but now you know the basics of what we're doing. Just very quickly, some of the work that we've done has used nanoparticles instead of cavities. So the thing about the cavity is that you have a resonance, but you can also use something like a plasmonic particle to have a resonance. A plasmonic particle has a plasmon resonance. This is now a lot broader, but the advantage is that the whole thing is very small, so the mode volume is already extremely small. And over the years, we've done a lot of work with that as well. The thing with the plasmonic particles and antennas is that you have to have near field coupling. So you have to really bring your antenna and nanoparticle very close to your molecule. And close means only a few nanometers. And so the approach that we've had in many of the projects is to use a scanning probe technology to literally pick up a nanoparticle and bring it and scan it across a molecule. Or again, grow things like a nano cone of gold using FIB and putting a molecule or a quantum dot at the end of a fiber and then bringing it very close and coupling. And this movie gives you a flavor of the kind of thing that now happens. You can see here that we can use piezo electrics to move these things against each other. So you literally have nanometer precision in positioning the molecule and the nanoparticle with respect to each other. And you see here is that when they are really within the very small distance, then the fluorescence is enhanced by a large factor. You can also get to the strong coupling regime at room temperature if you're in this regime, but I won't go through the details of that right now. If you talk about antennas, antennas are also very useful in directing light, not just enhancing the interaction. And here we developed what we call a planar antenna. It's not plasmonic, but it's a certain layer of dielectrics that affects the radiation of an emitter or a molecule in it and prevents the molecule from emitting in all directions, but forces the molecule to emit only in one direction. And that's important because usually, if you have your single photon source, so you have your atom, if your optics only collects a certain solid angle, then you're missing a lot of the photons. So even if your atom kind of sends photon every, let's say, nanosecond, you will be missing many of them, and that happens in a very random way. So it kind of spoils your quantum source. And what we showed was that with the antenna that I showed you, we can really get to a very high efficiency of collection so that in most cases, the photons come in the tack that we gave it. So you can excite the molecule at a certain repetition rate, and then you expect a photon every time you excite it. And what you see here is on this chain that, for example, in this regime, every single time there is a photon, once in a while one is missing, and that's because the detectors are not perfect. So still it makes it Poissonian, but with this we showed that we get to a certain degree of intensity squeezing because the randomness, or you're well beyond kind of below the short noise limit, because these things are not random anymore.
This is spontaneous emission, right?
This is spontaneous emission.
Spontaneous emission is simulated by the zero-point fluctuation photon, which is random. So you shouldn't expect the correlation between excitation and emission.
No, but the spontaneous emission only happens if it goes to the excited state. And whether it goes to the excited state depends on whether you excite it. So you excite it, you know that I excited now, and within the next few nanoseconds, something has to come out. You don't know exactly when, right, but you don't know exactly when, but between this excitation and the next one, you're sure that something comes out.
So your timing accuracy is within the decay time.
Exactly.
Spontaneous decay time.
Exactly.
Go within that,
No. Right. You don't, you get this Fourier limited kind of
light that comes out, but the bandwidth is given by the lifetime of the excitation. All right, so the last bit, I want to tell you a little bit about the work that we have ramped up mostly in the past 5 to 10 years. Before that, we almost did nothing. I went in the biophysics direction. But what we're trying to do is we try to basically import whatever techniques that we know in the lab and see whether we can do something useful in the area of biophysics. Mostly, we concentrate on either microscopy or sensing issues. So one thing that we do is try to get super duper resolution. So resolution is an important aspect of microscopy. You know that there is now super resolution, and within the diffraction limit, you can have a resolution of the order of 100 to 200 nanometers. With super resolution methods like STED, Palm, Storm, you have gone to about 10, 20 nanometers. But if you think about individual atoms, there's another 2 orders of magnitude to bridge. So there's a lot of work for people to do to bring optical microscopy to the regime that is usually only for X-rays or electron microscopy. But there's no theory that prevents you from going further in this direction. And one of the things that, or the thing that makes super resolution in its current form limited to about 10 to 20 nanometers is shot noise. That is, you collect a certain number of photons and then the molecule bleaches. You can't collect more. If you could collect more, your averaging would become better and better and better, and your resolution would become better and better and better. And we went about this problem by cooling down and basically slowing down photochemistry, which is responsible for photobleaching. So by going to low temperatures, which is what we had learned from these other work that I showed you, we've managed to reach angstrom resolution. And these are 2 of the examples of what we can do. This is a single protein that is labeled with 4 dye molecules sitting at only about 2 nanometers apart. And this is a protein complex. And in each case, wherever you see the red blob, that's what we have resolved. And the red blob shows the uncertainty with which we can find the position of that molecule. But again, this whole thing is smaller than the resolution that you would have in a normal room temperature type of thing. But this was done still with fluorescence, and generally you want to go away from fluorescence if you can, because there's lots of problems with it. One is that you first have to learn how to label things. 2 is that it will photobleach at some point, and the signal is intrinsically low because 1 poor molecule can only be cycled at a certain rate. You can't go faster than that. Okay. So we go back to our scattering issue. And I've talked to you about this before. The problem is the same as before. Instead of having a 2-level atom, now I just have generally a scatterer. My equation is still the same. I have a certain cross-section. I have a certain confinement in terms of my light. And how effectively light is coupled to that depends on sigma divided by A. And if I look in transmission, I should see a shadow. And now the question is, how strong is this shadow? Right? So if you look at a nanoparticle, then you see that it's the strength of the electric field that's scattered by it is proportional to the incident field and this polarizability alpha. Polarizability alpha scales with the volume of the nanoparticle. And of course, it has to do with the dielectric function of the particle and its environment. And when your particle becomes very small, you see that the volume part drops very quickly. And at some point, you don't have a lot of signal from it. And what we realized now more than 20 years ago is that we can still detect this nanoparticle if we just look at the light that's reflected somewhere from an interface and the light that's scattered by the nanoparticle. And again, that's nothing but the extinction formula that I wrote you before. So it's a coherent interaction of the light that's scattered and the light that is reflected or the light that is transmitted. And the thing now is that usually when you do dark field microscopy, you try to collect only the intensity of the light that's scattered. And the key in dark field microscopy is try to eliminate the incident light so that you can only see the scattered light. But this scattered light, because it's the square of the electric field, drops as a 6th power of the particle size. So the difference between a 10 nanometer particle and a 100 nanometer particle is 1,000,000 times in dark field. That hurts. That's at some point, you can detect a 100 nanometer particle very easily in dark field. You cannot detect a 10 nanometer particle.
This is not absorption, right? This is really scattering.
This is scattering. So this cross term also, of course, drops, but it drops as a factor of with the 3rd power. So it drops more softly. And now, of course, you have to worry about, what kind of detector you have and what kind of noise you have and all of that. And it turns out that in practice, it's much easier to detect this than to detect this. And this is what we learned many years ago. Again, the arrangement is kind of the same. This is what a normal extinction experiment would be. You focus the light onto your molecule or nanoparticle and look in transmission and you see a dip or a shadow. But what you can do is also, if your dipole is sitting at an interface the way it is, for example, for a microscope, biological sample, the light that comes back is going to be acting just like the light that is transmitted, and you're going to get the same equation as before. So I just show you that, at some point we realized that a virus is nothing but a nanoparticle. In fact, a fairly large nanoparticle of several tens of nanometers to a couple of 100 nanometers large. You all probably know that corona is about 110 nanometers in diameter. So it's a pretty large particle and light scattering can detect it. Again, in dark field, it's a little more difficult. But in ISCAT, the way I showed you, you saw here, it's quite doable. But the ultimate thing when you're doing biological sensing is to detect proteins or much smaller molecules. But remember that the polarizability scales as volume, which means that if you go, for example, a virus is a small nanoparticle, but a protein is much smaller. And the diameter of a protein is roughly 10 times smaller than the diameter of a virus, means that the signal from a protein is about 1,000 times smaller. So just because you can detect a virus doesn't mean that you can detect a protein. You have to work a little harder to get that signal done. We tackled that and it happened to be manageable. So here's now just the result of a typical kind of protein sensing experiment. You do this interference experiment, you have a cover glass, you might have functionalized this cover glass, but then we come with a pipette and introduce some proteins. And as the proteins come out of the pipette, we watch them, how they land here. Right now, the pipette is not opened yet, and what you see is the kind of noise that we have. But at some point, you will see here that the valve was opened, and these individual dark spots that appear, they're footprints or shadows of individual proteins as they come and land on the surface. And of course, because they come one at a time, we can actually figure out exactly where they're sitting afterward. This is a much, much more sensitive way of going about it than all the other sensors that are around, for example, plasma resonance sensors and things that are used commercially. One can actually show that
the size of this shadow is because it has to do with the polarizability and is proportional to volume, scales with the size of the protein or mass of the protein. So this has now become a very exciting way of augmenting mass spectrometry using light. And technique is sometimes called mass photometry.
Sorry, I missed the connection between the spectroscopy and how do you get the mass from light scattering and the mass?
So if you assume that the density of proteins are the same, then mass is going to be proportional to the volume. And our signal is proportional to the field, which is proportional to the polarizability, which is proportional to the volume. So the signal that we see, the contrast that we see, is directly a measure of the mass.
You have to know the density.
You don't have to know the density. You make something like a ladder. This is also what a lot of the other methods do, like electrophoresis or whatever. You end up doing an empirical ladder. And then after that, you read where you land on this ladder. Recently, we showed that we can now go back up to nanoparticles. And there are a lot of applications where people want to know something about nanoparticles, for example, in colloids or in impurities or in blood or whatever. And there are lots of different techniques of how to do that, in particular, dynamic light scattering. What we're showing here is that by looking at the trajectory of a nanoparticle using iSCAT, we get a remarkable sensitivity. And when you put the information about the diffusion of the particle and the optical signal of it, we have a very high resolution in deciphering mixtures of different nanoparticles. For example, here you see that it was a mixture of 40 nanometer gold particles, 100 nanometer polystyrene, and 100 nanometer silicon. And they all are separating very, very nicely in this 2D scatter plot. Here you see that there's a 30 nanometer gold particle, 20 nanometer gold particle, and 15, and they're also very nicely separating from each other. The previous techniques kind of look like that. They're not resolving this type of fine difference. This paper just came out, so unfortunately, don't have time to talk about the details of that. But next week, when I talk in chemistry, we can say more about that. And finally, we got the guts to actually do some cell work, which is now quite routine in the lab. The idea was that you want to actually see a protein diffusing on a cell. The cell background is too busy as a scattering medium for us to be able to pick out this tiny signal. So we're labeling a protein with a gold nanoparticle. And the gold nanoparticle is also small, but much more strongly scattering than a single protein. And we still had to learn how to see and track a nanoparticle on a kind of a wobbly type of background. So you do a little bit of image analysis, you extract the data, and then you can map trajectories. This is now an example of the kind of trajectory that we can record. I'll be done before that. And the thing that you want to note is that this is 100 nanometers. So the steps that this particle is taking are in the range of 2 to 3 nanometers. And we're recording at a very fast speed of the order of 50 to 100 kilohertz. So the result is that we can look at high quality statistics of this type of a trajectory in a very small region
that is of the order of a micron. And this is very exciting now if you want to understand cell membrane dynamics. And finally, we have shown now in a manuscript that's on arXiv, but it hasn't appeared yet, that you can do microscopy using this type of interferometric scattering technique in the cell without a label. Because inside the cell, you have vesicles, you have tubules, you have nanostructures that also scatter light. And if you learn how to pick out that signal and mask the background, then you kind of have the best of all worlds in terms of microscopy. So here's an example of how endoplasmic reticular tubules are forming dynamically. And you can also see that there's some vesicles that are jiggling around. These are all things that are not visible in a normal microscope. Of course, you can do them, you can see them in fluorescence microscopy, and we do benchmark all of these things with simultaneous fluorescence microscopy. But fluorescence microscopy has the usual problems that after the first few seconds, things are bleached, but then we can keep looking. So you can now look at things that go on for hours instead of seconds. And this is another last example of how you can actually look at a virus moving around inside the cell. Again, this is a virus, and that's an actin tail. And we know these things because we can label them with fluorescence. So these are all viruses that are in this cell. This cell was infected before. And now you can see that even without fluorescence, you can actually chase. I don't know where you are, you can see this, but you can see this virus, for example, is running around. There's another one here. So we're now gearing up to really try to develop protocols where we can understand how a single virus attacks a single cell, goes inside, makes the cell produce more viruses. Those viruses come out and infect the neighboring cells. Each one of these steps is quite complicated and not very well known right now. And you have a platform where we can do the imaging, you have a chance to have a quantitative understanding. So in this paper, if you want to know more about this, I mean, this is already by now, again, 3 years old, but a review of this type of technique and what we and other people have done. And with that, I thank you very much for listening. I'm sorry if I went over.
Wow, amazing results. Thank you. Let's see, I have 50 more questions, but we'll save this for dinner. Any questions from the audience?
Well, I'm just curious. So for the first part, you're talking about using the single molecule to kind of to do the operation. So I'm curious about the European really did some like operation to show that your skin can do something on the quantum circuit.
No, we're very far from that, and in a way, we're not. That's not really our aim. The molecule that we have is really not ideal for that. I showed you that, it has many levels and we have to work very hard to make it even a 2-level system. But even if a 2-level system is not an ideal kind of system for doing quantum operations, because the time that we have is only within the coherence time that we have is within the time of the upper state, which is only a few nanoseconds. So if you wanted to do operations, we would have to do everything extremely fast. People who usually do these things, they work with systems that have lifetimes of microseconds or milliseconds so that they have a chance to actually do something with it. And examples are color centers in diamond or certain types of quantum dots. These molecules don't have that. We are pushing, trying to see whether molecules can also have that functionality via the vibrational levels. But right now, we're not there.